In this video, we are going to learn how to differentiate functions using some basic derivative rules, including the constant rule, the power rule, constant multiple rule, and the sum and difference rules for differentiation. We are also going to learn how to take the derivative of sine and cosine functions, and finally, we will be applying derivatives to determine rates of change. We get started with 6 derivative rules. The first one, the constant rule, tells us that the derivative of any constant is equal to 0. So the derivative of just a number is 0. The power rule tells us how to take the derivative of x to the n power. The constant multiple rule tells us that if we're taking the derivative of a constant multiplied by a function, or a function divided by a constant, that we can pull that constant out and only focus on the derivative of that function, and then just multiply that by whatever constants we had. The sum and difference rules tell us that if we're taking the derivative of a sum or difference of two functions, that we can take those derivatives individually and then add or subtract them. The derivative of sine is cosine, and the derivative of cosine is negative sine. Now let us apply these rules to start taking the derivatives of some functions. In example 1, we start off with the function h of x, which is a sum of two separate functions. So to take h prime of x, we could first apply the sum rule, which would tell us to take the derivative of the first term, x to the 4/5, and to add that to the derivative of the second term, which is simply 7. So first I applied the sum rule. Now, to take the derivative of this x to the 4/5, I'm going to use the power rule, which tells me that I take that derivative by bringing the exponent of n down in front of 4/5. I still have x, but the new exponent on x needs to be n minus 1. So the new exponent is now 4/5 minus 1. So here we have applied the power rule. Now to take the derivative of 7, the constant rule tells us that the derivative of any constant is equal to 0. Now let's continue simplifying this. This is then 4/5 x to the negative 1/5. I don't have to write the plus 0. And the last thing I'm going to do is rewrite that x to the negative 1/5. I'm going to rewrite it with a positive exponent by putting it in the denominator. Furthermore, I could rewrite this without any radicals because x to the 1/5, without any fractional exponents, and instead using radicals because x to the 1/5 is the same thing as the 5th root of x. And there we have our derivative. In example 2, we start off with a function that is a difference. So in order for us to take p prime of x, I can start off with the difference rule. I will first begin though and just rewrite this term right here. This 1 over x to the 5th. I'm not taking any derivatives yet. I'm just going to rewrite that as x to the negative 5. So this and this are the exact same thing. No derivatives. And the reason that I did that is because now I can take the derivative of this x to the negative 5 using the power rule, because now it looks like x to the n. So when we have expressions that look like that, particularly with a constant over a variable to some power, the first thing we're going to do is we are going to rewrite it. Now that we have it rewritten, we can begin to take the derivative, p prime of x, by taking the derivative of each term and subtracting those derivatives. Now let's actually begin to differentiate. The derivative of 3 is simply equal to 0 using the constant rule. The derivative of any constant is 0. And then we have this minus sign that was already there. Now let's start to take the derivative of x to the negative 5 using the power rule. The power rule tells us to bring the exponent of negative 5 down in front and to decrease the exponent of x by 1, which now leaves us with a positive 5, because two negatives make a positive, x to the negative 6, which I will rewrite as 5 over x to the 6th. In example 3, I will first begin by rewriting this I have this 1 over the 4th root of x squared. First things first, I can rewrite this because this is the same thing as x to the 2/4. Generally speaking, x to the a over b is the same thing as the bth root of x to the a. We learned that in pre-calculus. I'm just going to simplify this very quickly because 2 over 4 is the same thing as 1/2. And then again, similar to what we did here in example 2, where we rewrote this so that we could take the derivative of it using the power rule, I'm going to rewrite this as x to the negative 1/2. Now I'm going to come in and take my derivative. I want to know what is the derivative of x to the negative 1/2. The power rule tells us to bring the exponent of negative 1/2 down in front and to decrease that exponent by 1. We then have negative 1/2 x to the negative 3/2. And the last thing I will do is rewrite that so that I don't have that negative exponent. So I still have the negative 1/2, negative 1 over 2. But as for this x to the negative 3/2, it's going to show up in the denominator, and I'm also going to write it as a radical. So I have the square root of x cubed. I don't typically write that little 2 out there for square roots. Example 4, we want to take the derivative of 3x. Well, we are taking the derivative of a constant of 3 multiplied by a function of x. Please do not get confused here and think that because we have that constant of 3, we need to be using the constant rule to say that derivative is 0. The constant rule is only applied to constant terms, like 7 or like 3. It is not applied to variable terms like 3 multiplied with an x. This 3x looks more like this CF of x. And when we go in to take the derivative of that, the constant multiple rule tells us that I can pull this constant of 3 out in front of the derivative operator and be left with 3 times the derivative of x. Then to take the derivative of x, which is x to the first power, we can use the power rule. So we still have this constant of 3 out in front, and the power rule tells us that I need to bring the exponent of 1 down in front, and the new exponent on x is 1 minus 1. Well, 1 minus 1 is 0. And anything to the 0 power is equal to 1, and so this is simply equal to 3. I will mention briefly, as we get more comfortable taking derivatives, I typically will not be continuing to write this derivative operator, being that this is our first time taking derivatives without going through this long, drawn-out process from our previous lesson. Because remember, before, the only way we had to calculate the derivative was for us to calculate this limit. That's how we were calculating derivatives back in 2.1. 2.2 comes in and gives us a handful of rules that we can use to get the derivative a lot quicker. Generally speaking, we will not always be writing these derivative operators and taking this step by step. As we get more comfortable taking derivatives, you'll be able to jump in a lot quicker. Example 5, I'm going to begin by simply just rewriting this function. I have that exponent of that negative exponent in the denominator, so I'm going to rewrite it by bringing it up to the numerator and making it a positive exponent. Rules of exponents tell me that I need to cube the 2 and also cube the t. And so we are left with 56t to the third. That is not a derivative. That is the exact same function. All of these are equal. This is still the original function, g of t. To take g prime of t, I'm going to come in and apply my derivative operator. The constant multiple rule tells me that I can pull that constant of 56 out in front of the derivative operator. Power rule tells me that to take the derivative of t to the third, I drop my exponent of 3 down in front, and I decrease the exponent on t by 1. So the new exponent is now 2. Multiplying 56 by 3 gives us our final answer of 168t squared. The first thing I'm going to do in example 6 is rewrite the radical in the denominator as a fractional exponent. Now I'm going to rewrite this expression. So instead of looking at a constant over this variable term, I'm going to bring that variable term up to the numerator and change the sign of the exponent so that we can more easily use the power rule. Now to take p prime of y, I'm going to come in and apply the derivative operator. Notice that I am using a variable of differentiation of y. Constant multiple rule tells me that I can take this -4 out and pull it out in front of the derivative operator. Now with what we are left with, we are going to apply the power rule to take the derivative of y to the -7/5. The power rule tells us that the exponent of -7/5 comes down in front, and the new exponent on y needs to be 1 less. I'm going to multiply here to get a positive 28 over 5, straight across the top, straight across the bottom. -7/5 minus 1 is a -12/5. And now I'm going to rewrite that without the negative exponent by sending it back to the denominator. And I'm also going to write it as a radical instead of a fractional exponent. So when we simplify our derivatives completely, that is what we're going to make sure to do. The two things that we are going to be looking for is we want to see positive exponents and we want to see no fraction exponents. To be clear, it is not that this version is incorrect. That is also correct, but this is a more simplified version that we will be using. In example 7, we're going to begin by applying the derivative operator to each term of this function. In the first term, the constant multiple rule tells us that we can pull that constant of -5 out in front. And I want to correct my notation here. I should not have f of x. I should have f prime of x because we are now taking the derivative. So back to where we were, I'm going to pull this constant of -5 out in front of this derivative operator. In the second term, I am going to pull the constant of 2 out in front of the derivative operator. And in the last term, the derivative of 9 is simply 0, and so I will put a -0 here. Back to the first term, to take the derivative of x squared, we will use the power rule. So our constant of -5 stays with us. Power rule says bring the exponent of 2 down in front, and the new exponent on x is 1 less, which is 1. I'm going to take the derivative of x in a similar way. You may remember that we took the derivative of x back in example 4, and the derivative of x is simply 1. So this is 2 times 1. So we are left with -10x plus 2 as our derivative. In example 8, we have a quotient, but we have not yet learned the quotient rule for derivatives, and we don't need it to take the derivative of this expression. We're going to first start by simplifying this function by breaking it up into 3 separate terms. Each term will be divided by what we have in our denominator, which is 3t. Now we can simplify this expression term by term. In the first term, one of the t's will cancel and leave us with 4/3 t. In the second term, the t's will cancel and simply leave us with 2/3. And in the last term, nothing cancels, but I will rewrite it as 1/3 t to the -1. Now I am ready to come in and start taking the derivative of g by applying the derivative operator with respect to t to each 3 of these terms. Now that we have that applied, constant multiple rule tells us that we can pull this constant of 4/3 out in front of the derivative operator and be left with only the derivative of t. In the second term, the derivative of a constant is equal to 0 from the constant multiple rule. And in the third term, we can similarly pull out the constant of 1/3, leaving us with the derivative of t to the -1. The derivative of t is 1. I don't need to continue to write that -0. In the last term, we still have our constant of -1/3, And as for the derivative of t to the negative 1, we're going to pull down the exponent of negative 1, and the new exponent on t will be negative 2, because we subtracted 1 from negative 1. So we are left with the derivative of 4/3 plus t to the negative 2, and I will rewrite that as 4/3 plus 1 over t squared. The first thing we're going to do in example 9 is rewrite the first term so that we're not looking at that fraction and we instead see an expression on which we can apply the power rule. So I did that by bringing this y to the 1 up to the numerator and making its exponent now negative. Now I'm going to come in and apply the derivative operator to each term. Now I will be applying the constant multiple rule to the first two terms and pulling those constants out in front of the derivative operator. In the third term, e is a constant and the derivative of e is simply 0. Now in the first two terms, I will be applying the power rule to take the derivative of these power expressions. In the first term, the exponent of negative 1 comes down. I decrease the exponent by 1 so that it is now negative 2. In the second term, the exponent of negative 4 comes down. I decrease the exponent by 1 so that it is now negative 5. And now we simplify. The last thing I will do is rewrite this expression so that it has no negative exponents. In example 10, I will get started by applying the derivative operator. This is our first example that we're seeing with a trig function, but that trig function does have a constant in front of it. Constant multiple rule tells us we can pull that constant out in front of our derivative operator and only focus on taking the derivative of cosine x. I'm going to pop up so we can see our derivative rules. The derivative of cosine x is negative sine x. So I will now be replacing this derivative with cosine x, this derivative of cosine x with negative sine x to leave us with our final answer. In example 11, I will get started by applying the derivative operator to each term. In the first term, I'm going to use the power rule to take the derivative of theta to the 6. I'm going to pull the exponent of 6 down, and the new exponent on theta will be 1 less, which is 5. In the second term, I'm going to apply the constant multiple rule to bring the coefficient of 6 out in front of this derivative operator. Notice that the derivative operator does have d theta, since the independent variable here is theta. Once again, the derivative of cosine is negative sine, so we have 6 theta to the 5th minus 6 times negative sine theta. And the last thing I will do is simplify because we have a negative negative, which will combine to give us a positive 6 sine theta. In example 12, first thing I will do is fix this typo where I want to have a t right there instead of an x. I'm going to begin by just rewriting the function g of t as 1/2 times sine t. And just rewriting, instead of writing that division by 2, I'm just going to write it as a constant times that trig function, because then I can see more easily how we will be applying the constant multiple rule. I first come in and apply my derivative operator. All this does is this tells you to take the derivative of what's on the inside. That's all that means. Rules tell us, well, hey, before you do that, you can pull this constant of 1/2 out in front of your derivative operator and only take the derivative of sine t. Going up to our rules, we can see that the derivative of sine t would be cosine t. So I'm going to replace this with a cosine t, and we are left with our final answer. The next topic that we will discuss is rates of change. The derivative can be used to determine rates of change. For example, things like water flow rates or production rates if we're working in a factory, or how fast a population is growing. An example that we will look at today are velocity and acceleration. Before we can discuss that, we must first discuss what a position function is. And a position function is a function that gives us the position of an object. It tells us where an object is relative to where it started at some time. So for example, in example 13 here, we have a ball that's been dropped from a height of 55 feet, and we have a position function that tells us where the ball is at a certain time. What we want to do is we want to find average velocity on these intervals. And average velocity is the change in distance divided by the change in time. So in order to find the average velocity, the average speed of the ball as it fell on the interval from 1 to 1.5, I would need to know, well, where was the ball after 1.5 seconds? And from there, I will subtract the position of the ball at 1 second. So this numerator is the change in distance, the change in the position. In the denominator, I do the change in time. Well, the time that we're interested in started at 1.5 and ended at 1. This leaves us with 19 minus 39 in the numerator over 0.5 in the denominator. So I'm getting these numbers by simply plugging 1.5 into this position function, and similarly from plugging 1 into this position function. And we are left with negative 40. And let's consider our units here. The numerator came from the position function, which is measured in feet. And the denominator came from the independent variable of time, which is measured in seconds. So this is 40 feet per second. I'm going to similarly work through example 13b. So we have this all plugged in, change in y over change in x, and this leaves us with negative 33.6 feet per second. I will point out that both of these answers are negative because this ball is falling. The last topic we have are the concepts of velocity and acceleration. Velocity is the derivative of the position function, and acceleration is the second derivative of the position function. Equivalently, it is the first derivative of the velocity function. Example 14, we are given a position function for a ball that has been thrown into the air. We want to find the height, the velocity, and the acceleration of the ball when t is equal to 2.5 seconds. In order to find the height of the ball at 2.5 seconds, we need to plug 2.5 into the position function, because that will give us the position, the height of the ball after 2.5 seconds. And that tells me that after 2.5 seconds, the ball is 140 feet into the air. Now, to find the velocity of the ball after 2.5 seconds, we first need to find the velocity function. So I'm going to begin by finding v of t, the velocity function, which is the derivative of the position function. So we're going to be taking the derivative of this function. I'm going to take the derivative term by term. The first term, we have that negative 16. That's a constant, so I'm pulling that out. And then we're going to take the derivative of the t squared. To take that derivative, we pull the exponent of 2 down, and the new exponent on t is 1. Moving on to the second term of 48t, there's a constant of 48, which can come out. I'm left with the derivative of t, and the derivative of t is 1, which I'm not going to write. And for the final term, the derivative of 120 is simply 0. So now we know that our velocity function is equal to negative 32t plus 48. Now I'm going to evaluate this velocity function at 2.5. leaving me with negative 32 times 2.5 plus 48, which gives us a negative 32. And velocity is measured in feet per second in this case. This is a change in y, a change in feet over a change in x over a change in seconds. The final thing we are looking for is the acceleration after 2.5 seconds. To calculate the acceleration, we are going to need the acceleration function, which is the second derivative of the position function, and equivalently, it is the derivative of the velocity function. So now we are taking the derivative of this velocity function. Taking the derivative term by term, starting with the negative 32t, the derivative of the first term is negative 32, because the derivative of t is simply 1. And then for the second term, the derivative of 48 is 0. And so this is our acceleration function, simply a negative 32. If we were to evaluate that at 2.5 seconds, there's nothing to plug in, and we are simply left with negative 32. This unit is feet per second squared. So we have calculated our acceleration, we have calculated our velocity, and we have calculated our height, all at 2.5 seconds.